Hello. So here is a small explanation on the mini exploration that you will have to hand in, and it has to do with optimization and the tiger's fastest path. So we have a tiger that is on this side of the river, and the tiger wants to swim first and then run to reach the buffalo. We will assume that the width of the river is constant and that the tiger's speed when it swims, it's also constant, the same as when it runs. So our task is to explore the position of the optimum landing point X so that the time it takes for the tiger to reach the buffalo is minimum. It's an optimization problem again. You will be assessed on the following criteria, and there is a document uploaded under your assignment where it explains what each of those criteria is. First, communication. So how organized and how concise and coherent your exploration is. Mathematical presentation. Are you using the proper notation? You're using good diagrams, graphs, where you annotate your axes and everything is in place. The personal engagement, how much you take initiative to explore the problem further, how much you introduce the reader into it. The reflection, how you interpret your results and how you explain your results to the reader. And of course, the use of mathematics, whether or not the mathematics you're using is correct. So you can read about the criteria and ask me further, but now let's start solving the problem. So you have to write an exploration, and I have written down some steps here that will probably help you out. So first, it would be a good idea to present the problem to the reader and make some assumptions. And that's the river, and you have the tiger over here that wants to cross it and reach the buffalo. So the tiger is going to swim this distance and then run. So it would be a good idea if, for example, we consider that this distance is B, so from A to B, maybe we can call it B, and this small distance here is X, right? Lowercase x. And then maybe that's the width of the river. And we can directly go and write that this distance from T to X, from the tiger to the landing point X, will be square root of the width squared plus X squared. Just so we have all the variables in place. And then we can say that the tiger swims. You could assume that the speed is 1 meter per second. You can also assume a different speed. That's up to you because this is your project. And the speed that the tiger runs, I wrote here, it's 4 times more. But again, it's up to you. It's your project. I also assumed that the width of the river is 5 meters. So the tiger wants to reach the buffalo in the shortest possible time. We have presented the problem, we have made a clear diagram, we have made assumptions, and now we can start solving it. So first, let's find an expression in terms of the problem's parameters. So here we need to minimize the time it takes. So let's find an expression for the total time. And I wrote here that the total time that it would take for the tiger to reach the buffalo is the time that it takes to swim plus the time that it takes to run. And you know how the time is distance over speed? And that's what I wrote here. So it's the distance that it takes to swim over the speed that it takes, the speed of the tiger when it swims. So, as I promised before, this distance is going to be the square root of w squared plus x squared. So here, that's the swimming distance, and this is the swimming speed. And the running distance is going to be b minus x over vr. So this is now an expression of the time in terms of x. X is the landing point, right? So x is this distance here. And that's what we're trying to find here. So this is an expression for the time. Remember, the swimming speed is constant. The running speed is constant. It's up to you to assume. B is the distance where the buffalo is sitting. You can also assume that value, no problem. Here I should have written W, sorry. That's the width of the river, which is also constant. So in a way, we've got an expression where x is the unknown, that's the landing distance, and that's the total time it takes. So if you use your own values for the running speed, the swimming speed, the width of the river, and so on, how does it look? That's a step 3. Use graphs to show what you found. How does it look if you plot the time, the total time, as a function of x, the landing distance? And maybe it will probably look like this. And then you can see directly that at this x0, we'll call it, at this specific landing distance, the time it takes for the tiger to reach the buffalo is the shortest. So depending on the values that you will choose, you will find a specific landing distance over here, right? Of course, you will have to, probably it will look like that, I don't know. Of course, you will have to talk about the domain and the range. You cannot have negative times over here. Negative distances and negative times, right? So you have to take care of the domain and the range. So can we use another method to reach the same result? So you have now basically figured out what is the landing distance in order to reach the buffalo at the shortest time, because that's when you get your minimum time. And also maybe you can ask yourself, what is the minimum time? Can we use another method to reach the same result? Well, we have learned calculus. And if this is the expression of the total time that it takes for the tiger to reach the buffalo, we discussed that when you take the derivative of this expression and you set it equal to 0, you will also find either minima or maximum. So here, how can you take the derivative? Well, let's look at the first part here, where you have w squared plus x squared over vs, and that's the top is to the power of a half. Remember how, that's the derivative, that's what you want. Remember how w and vs are constant numbers. So when you take the derivative of this would become a half, would go in front. And remember, the vs is also a constant, so it would become a half times, maybe we can write it like this. 1 over vs, well, that's the constant, times a half v squared, w squared plus x squared to the power of negative a half, because you reduce by 1, times the derivative of this. So keep this in mind, because now we can rewrite the derivative as 1 over vs times a half times w squared plus x squared to the negative half times the derivative of w squared plus x squared. However, w is a constant number, so its derivative is 0, and the derivative of x squared is just 2x. So this is the derivative of the first part over here. Now what about the second part? Well, plus this is constant again, this is constant, so 1 over VR can go out, and the derivative of b minus x is going to be negative 1. And you can rewrite this as 2 cancels out, and you will have x divided by vs times the square root of w squared plus x squared minus 1 over VR. So this is now an expression of the derivative of the total time it takes. You can see now that the derivative depends on x, which is the landing point, the landing distance, that's what we want. Vs is constant, is the swimming speed. VR is constant, is the running speed. And W is the width of the river. And if you set it now equal to 0, and you start solving, we will be able to find the landing distance x in terms of the speeds and the width of the river. We could do it by squaring both sides. And we need to solve for x. So try to do this, and you will end up finding an expression like me over here. So you can see now that x, the landing point, depends on the width of the river and the ratio of the two speeds, the running and the swimming speed, squared. So what does that mean? Does this confirm the previous results that we found? We have to reflect and explore and explain what we found. Another step 6 could be, if you set the ratio of the speeds as r, you could rewrite the equation 1 as, how can you write it? Plus minus the width of the river divided by the square root of the ratio of the speed squared minus 1. And now you could see, how does x vary with the ratio of the speeds? Can we make a graph? So how will it look like? And for what ratio of the speeds the landing point x is the shortest or the largest? You have to explain what's the domain of the graph and what's the range. You can see here r cannot be, for example, 2, because it could not be a number less than 1, because if that's the case, you will end up with a square root that it will have a negative number underneath, and that's not allowed. So you have to really reflect here to explain what happens mathematically, but what this also means in a physical context. So what does it mean? Reflect. Step 7, you could explore it even further. We discussed in class that when the second derivative is positive, remember, at the point of interest, there is indeed a minimum. Is this the case? Maybe you can try and find the second derivative at your point and see, is your second derivative positive? Then it means that it's a minimum. and so on and so on. So you will be assessed in those criteria: communication, how structured your investigation is, mathematical presentation, are you using appropriate graphs, appropriate notation, and so on. It's very important that you reflect on your results, that you explain to the reader what they mean, and you take it a step further. And it's actually very hard to score in high marks in criteria C and D. Yes. So take a look, have a good start on your project, start writing it. It should be less than 10 pages, your final product. And you can use software as, for example, Desmos or GeoGebra to construct your graphs, or Autograph. Yes. So have a good start, and you're very welcome to send me any questions you might have, and ask the other teachers during the study cafe time as well. And that's it from me.